Number one, it's an interesting myth. Myth number one is CP and PP tell you if a process is capable. Now, you would think that they would because they call them capability indices. But the fact of the matter is that it's impossible to tell if you're capable with the CP and PP. Let me show you why. CP and PP are the ratios of the width of the tolerance to the width of the process variation. And that's it. It's simply the ratio of the two. And here's the calculation. As you can see, it's the ratio of the two. And you'll notice that there's no location function. No location function whatsoever. So that being the case, it could be either within or outside of the specifications. All of these examples have the same CP or PP because all it is a ratio. So by not having any idea of where the location of the distribution is, simply the ratio, you don't even know if the distribution falls within the specification, which is kind of a key piece of information if you're trying to determine capability. So really, CP and PP, even though they are ratios of what might be able to be capable, they are no indication if it actually is capable, and certainly no predictor of future capability. Myth number two is CPK and PPK tell you if a process is centered. And quite frankly, I fell victim of this myth myself, and it took me a while to figure out that this is really not the case. People realize that you can improve your CPK and PPK by centering your process variation. And you can see that from the example here. The more centered you are, the higher the value is going to be for the same process distribution. And because of that, people think that a better CPK or PPK value means it's more centered. And that would be nice to support the Taguchi loss function. However, that's not the case. If you take a look at these two examples, you'll see that one is nowhere near the center. The other one is nicely centered, but much wider. They both have the same capability value. So even though the top one has the same capability value, none of the distribution falls within the sweet spot, which is actually in the center of the specification. So it does not tell you, just by simply looking at a capability value, whether or not it's more centered or not. It really, as you can tell from here, has nothing to do with that at all. However, you can determine the percent non-conforming of the parts from your capability study, because CPK and PPK are actually Z values. And you can take that Z value and go into your Z value chart and determine what portion of the tail has a probability of being out of specification. That's nice if your distribution is a normal curve. Because as you see, it's specific to the normal curve. So if your values are in some other distribution, you can't use it directly. So it either has to be normal, or you can transform it to normal for this to be valid. And myth number three is, and the most important of this, is you are using sample data. It is virtually no predictive value whatsoever on these capability. If you take a look at the total variance equation, you'll find that there's a lot of characteristics that contribute to your capability, but your sample is a very small sample. Typically, you might have 125 pieces over a 300-piece run. The sample rarely contains enough of significant variation in raw material lots, variety of operators, machine wear, gauge wear, all those types of things to accurately predict future performance. So it does a pretty good job of telling you what the performance is, but has very little value in predicting future performance. And that's one of the problems that people that are utilizing capability indices run into. They actually believe that it does. So let's take a look at the unilateral tolerance capability as a case study. Unilateral tolerance is one that has a physical limitation that prevents a process from varying past a particular value. Form tolerances, roundness, flatness, runout, etc., are typical tolerances that it can exhibit a physical limit, usually 0. When a process output is in the vicinity of the physical limitation, it will not exhibit the normal distribution. And you can see that from this demonstration. The further away from the limit, the more likely it will behave as a normal distribution. So the worse you are, the more normal you will be. The better you are, the less normal you will be. So let's take a look at some possibilities on how one might approach trying to calculate capability for a unilateral tolerance. The first step is we're going to try to calculate assuming the normal distribution, and we're going to use 0 as a lower spec limit. There's a couple problems with this. First, if you were to assume the distribution was normal, using 0 as the lower specification limit, it forces the software to assume that the center of the tolerance is optimal. So it's going to calculate CPU and CPL, or PPU and PPL, from the center of the distribution. But that's not the case, because actually 0 is optimal, not the center. So this is incorrect. Using a normal distribution as a model for data when it does not fit is also statistically inappropriate. As we saw previously, as we get closer to 0, it's not going to be normal. Take a look at the test of fit here, 0.0974. A perfect fit is 1.000. If we can find a distribution that fits better, we're better off using that distribution as a model rather than one that fits so poorly. You cannot assume that the normal distribution is going to be the one that's the best model for this kind of data. Now notice that CPK and PPK are a measure of distance of the mean to the nearest specification. The problem when you have CPK and PPK calculated with 0 as a lower spec limit is it's going to calculate both directions, and that's not appropriate. You want to calculate from the mean over to the active specification, not 0. The closer the mean is to the specification, the higher the risk of parts being on the specification. So let's try calculating this without 0 as a tolerance. Now it's going to calculate from the mean over to the spec limit itself. I refer to those casually as half PPKs because normally when you're looking at a PPK, you're looking at the lesser of PPU or PPL. In this case, we're just going to use PPU and we're going to ignore PPL. So we're going to look at the distance from the mean to the upper spec limit, or PPU. The technique eliminates the problem of assuming the target value is in the middle of the tolerance. So that's good. The problem here is you're assuming the correct model is the normal distribution, and that's bad. Take a look again at that test of fit, 0.0974. So let's try curve fitting and finding a value or a distribution that is more appropriate for the data. We're going to try this first by having 0 as a lower spec limit. Again, that's not a good idea because the software is going to assume that the best spot's in the middle and it's going to calculate to both ends. So really, we don't want to do that, even using a fitted distribution. So the best approach is to not use 0 as the specification, to curve fit the best model to calculate the best estimate of the distribution of the data. In this particular case, you can see that they found the smallest extreme value family as a model for this data. Look at the test of fit. The p-value is 0.9949, almost a perfect fit. This is clearly a much better model than the normal. Now, what happens with this software is it goes in and it will transform it to normal to calculate these values, but it's transforming it from a much better model, and that's what you want. However, remember the caveats of the whole point of capability calculations. Even though we have a better capability calculation, it still falls prey to all of the issues we have with its predictability. So now we're going to take a look at a different capability. This is the capability in precision machining. Wow. I don't know why this is all messed up, because this is not what's supposed to be in there. Somehow this got chewed up. Hang on just a second here. See if I can bring up another value. I apologize. It worked fine before, but okay. If you saw this distribution, what would you think about this capability study? Most people would say, oh, gee, look at this. This is clearly bimodal. This process is totally incapable. There's two things going on. This is not good. How about if you saw this? Well, this distribution, people might say, well, it's skewed. So clearly, again, there's a problem. This is not capable, nor is it in control. Does a skewed or bimodal distribution mean the process is not capable? Most customer SQEs would say that that's true. However, and they would reject your PPAP based on that alone. The problem is, in this particular case, they would be wrong. In fact, both distributions came from the same capable process. And you might ask, well, how could that be? The problem is sampling error, not process variation. So what happens here is we're taking a look at precision machining. And precision machining, for example, in grinding, what we have is a wear and adjust type of a situation which generates a sawtooth curve. The sawtooth curve is not a normal distribution. It's not random about the mean. However, it is perfectly stable, and it's exactly what you would expect from a machining operation. If you take a look at the sawtooth curve, it generates a rectangular or uniform, continuous uniform distribution. It's not normal, and it's not supposed to be normal. So assuming that it's normal would actually be incorrect. It's the continuous uniform distribution. And that's what you expect. Now, to calculate capability for that distribution, now follow me on this, you're calculating the width of the specification over the width of the process variation. But in this case, the specification is upper spec limit minus the lower spec limit, but the process variation is the upper control limit minus the lower control limit. So if you set your control limits at 75% of your specification, you will get a capability of 133. Now remember, CPK, PPK, CP, and PP are all relative back to the normal distribution. So we don't call it that. but this is the true process capability for the uniform distribution. Now, if you wanted a 166, you would notice that you would have to run to 60% of your specification. However, if you were to do that, what it has you do is decrease the distance between your control limits, and that causes more operator intervention. More operator intervention is typically a bad thing. What you want is less operator intervention. So unless there's an economic reason why you must compress the control limits, it's not a good idea to do so. And if you want to do Six Sigma and get a capability of 2, you would only be running to 50% of your tolerance. But again, unless there is an economic reason why that's necessary, all you're doing is creating more operator intervention, more adjustments than are really needed. Now, here's the problem when sampling this type of a distribution. If you take a look at this sample, it took a nice sweet spot right out of the middle of that sawtooth curve. And if you take a look at it, this is a great way of generating capabilities of 12, 13, that type of thing. But as you can see, that's not truly the capability of the process. Again, it looks to be fantastic, but that is sampling error. You can also get sampling error by sampling in this particular location, which is just before the adjustment and just after the adjustment. Now, that sample would appear to have a bimodal distribution, but as you can see, it came from the exact same process. So really, even though you're seeing a bimodal distribution, that was not really from a process that was out of control and incapable. In fact, here's a whole variety of examples of the effect of sampling error on distribution histograms. You can have skewed on both ends. All of this is based on the sampling error, because the only true precise sample would be one right after the adjustment and right before the next adjustment. Oh, okay, well, so again, when you're doing precision machining, the capability actually goes back to the calculation of the specification limits, because those are the two locations that you are adjusting between. There's no need to calculate sigmas or that type of thing, because with a continuous uniform distribution, it's already known where it begins and ends. It begins and ends at the 2 points that you're adjusting between, which is your control limits. Okay, that was what we had left off from the last presentation. So does anybody have any questions concerning that?
Bob, are you able to see Henderson's question?
I'm getting to that right now. I'm trying to open up the.
Okay.
There we go. What is the purpose of PK? I guess I'm not familiar with PK. I know CP and PP. I'd have to take a look at my Both book, I guess, to see if there's a PK out there. I'm sorry, I don't. For Todd, are you an advocate of using Pearson curves? Actually, in essence, yes. My preference actually is to use a software that's designed specifically to do the curve fitting, which is called Distribution Analyzer, and that's from variation.com. I don't have any interest in it other than it works fantastic. And the reason why I like it is it's designed specifically to do what we just saw. And you can do these types of things in Minitab, but because Minitab is a toolbox and not a tool, sometimes when you want to do something, it really gets kind of messy. Whereas this is designed to do one very specific thing. You load your data in there as if you're doing a spreadsheet. You ask it to find the best curve, and then you have it chart it, and it will give you the same information that you saw on my presentation. It's actually simple, and you can't ask for anything better than simple. So it uses the Pearson curves and a variety of other curves to figure out which one is the best fit. So that's really the approach I prefer, but curve fitting is the way to go. CK, if it's not useful for predicting the behavior of a process, really it's not. You can use your capability indices to determine where your process is at. You can take a look at the snapshot in time and see if there's anything that you need to do to adjust it. Your best bet, of course, is to use CPK or PPK because you're trying to figure out, at least some relationship to the spec. Those are the only ones that are tied to the spec as far as a location. CP and PP, they don't. So quite frankly, I'm not sure outside of their academic value, what value they have at all. They provide maybe a potential, if you were to center it, what you might be able to get at a maximum. That's it. That's not a very powerful tool at all. Like I showed you, you can actually be totally away from your specification and still have a CP or PP. That's fantastic just because it's narrower than your specification. It's just simply a ratio. And remember, what's key to understand is, and it goes back, especially if you're automotive, you can go to the AIAG books. The CPK and PPK are specifically to be applied to normally distributed characteristics with the target in the center. So that's why when we're looking at things like toolware, it's not normal. We need to use a different approach. While we're using form, it's not normal. We need to use a different approach also. We need to use the correct approach, using the statistics correctly. Oftentimes people will use the, as I referred to, half CPK calculated with a normal curve for some of these forms, and it's not correct. And oftentimes you'll penalize yourself by calculating a lower value than you really should have gotten by using the correct distribution. And there's, when it comes to determining capability for, at least the snapshot in time that you are looking at, there's no point in penalizing yourself by using the wrong distribution to analyze it.
Hey, Bob, there's a question that's come up. I don't know if you see it or not. One of the participants is saying they cannot see any of your slides. Is that correct?
Let me jump back in here. Can you see it now?
Yes, thank you.
Let me minimize the ribbon. Well, without going through the whole thing, and there again, these will be posted. The key for the precision machining is the precision machining uses a sawtooth curve, which is where, adjust, where, adjust, where, adjust. and that gives you a non-normal distribution, the non-normal distribution, the continuous uniform distribution. And what happens is you're adjusting between these 2 points. Those are your control limits. So instead of calculating 6 sigma as this distance, it's actually just the distance between the upper control limit and the lower control limit. So if you want a capability of 133, you just use 75% of your specification. What's interesting about this particular capability is it actually is predictive. If you set up your control limits to 75% of your spec, and you are constantly adjusting between them, as you would do here, then yes, that's what it will do from now on. And the other beauty of that is you never have to recalculate because those are constants. That's another bonus. And again, if they didn't get a chance to see this one, oops. I wanted them to at least see how unilateral tolerances behave. That would be from current slide. As you can see, as it gets closer and closer to 0, which would be on the left, it gets less and less normal. And that's why you can't use the normal distribution as a model. Okay, so I'm going to jump off here and get back into the see if there's any more questions. Have you dealt with calculating CPK for true position with an MMC modifier? Whoa. I would probably not calculate CPK for a true position value with an MMC modifier. What I would provide is capability based on an attribute study. Because really, when you see a true position value with an MMC modifier, it is screaming out at you to use a hard gauge. You know, so as long as your part fits that gauge, you're good. Everything's built into that. So I use an attribute, which is tough, especially in automotive, which means every part has to fit it for your capability study, but that's what I would do for that. I wouldn't even attempt. First of all, again, knowing what little power capability indices have, I wouldn't spend the kind of time that some people do trying to figure something out like that, when really all you do is an attribute capability study. Does that help, Todd? You have any other questions?
Bob, it doesn't look like we're getting any questions at the moment. We can pause a few more seconds and see if anybody has any other questions. You're having to close your slides up in order to see the chat box, I'm assuming. That's probably why a couple folks are saying that they keep losing seeing your slides.
Yeah.
Not a big deal. Does anybody have any other questions for Bob? If you do, go ahead and type them in. As a quick reminder, the next webinar is the day after tomorrow. It is Military Generals, Mindfulness, and Emotional Intelligence with Susan Schwartz. And if you have not registered for it, we still have space available. we'd love to have you join us for that webinar on Thursday. Bob, it doesn't look like you're going to get any more questions. If people do have questions later that they don't, they're not thinking of right now, is it okay for them to contact you directly?
Absolutely. The best thing to do, the easiest one to remember, is just contact me at bob@correctspc.com.
Okay. Great. We don't have any other questions, it looks like. So we're going to go ahead and wrap things up for now. I'd like to thank Bob. We do have a question, looks like just came in, Bob. Can you see the one from CF?
Yes. Any foreign SPC techniques out there? I'm not from other countries, but it's statistics, so hopefully it all applies no matter what country you're at. I try to keep my thumb on the pulse of all of the SPC techniques that are out there, so we can make sure that we're giving you the most up-to-date and valuable information. I can't really think of anything right now that would fit into that category. Some of the things that I was looking at, even to prepare for today's presentation from other countries, I can't read it, but you can tell exactly what it's about. So they're all using the same type of information. So.
Okay, well, looks like that's probably about it for now. I'd like to thank Bob once again for coming back and offering the case studies on capability indices. And I'd also like to thank everybody for joining us a second time. For those of you who joined us both on the 24th of October and today, the certificate that you will be receiving will show 0.2 RUs, which would be twice the normal number of RUs that you would normally see. So it will also show both the October 24th session as well as today's. So with that being said, we'd like to thanks to everybody for joining us, and until Thursday, if some of you are joining us on Thursday, we'll see you then. Until then, hope everybody has a good rest of the day. Thanks very much. Bye now.